Good afternoon, ladies and gentlemen. My name is Anna Kiwilsza. I'm representing the Faculty of Physics at the Adam Mickiewicz University in Poznań, Poland. I would like to say a few words about the application of hexagonally arranged mesoporous silica materials for drug delivery. Experimental part of this work was done thanks to the equipment in Nanobiomedical Center, also in Poznań, and the part connected with the laboratory synthesis was done with in the cooperation with the University of Medical Science in Poznań. The outline of my presentation is the following. First of all, I would like to mention something about how the mesoporous silica materials were invented and when they were for the first time implemented in drug delivery. Then I will draw the aim of my project. Then I will characterize briefly my pure materials, I mean drugs and also silica matrices. Then I will say a few words about the encapsulation methods which we use in our laboratory. Then something about experimental analysis of our systems, and then I will I will do some summary. As an official date for inventing mesoporous silica materials, 1992 is considered. It was when the workers of Mobile Corporation from the USA for the first time synthesized MCM41 material using a three-block copolymer, ionic copolymer as a template. They didn't only synthesize the material but also confirmed that it has a hexagonally arranged structure of pores and also said something about its adsorption properties. But not many people know that more than 30 years earlier, the same synthesis was used in creating mesoporous silica to be used in photoluminescence application. Since 1990s, this kind of materials were widely used in catalytic application and also in pollution removal. After discovering that these materials are non-toxic and are very biocompatible, they were also used in drug delivery. For the first time, a group supervised by Professor Maria Vallet-Reggi used ibuprofen, a simple drug, and encapsulated it into MCM41 and showed that this kind of carrier can change the releasing profile to be more stable in time. Our project is divided into three main steps. In the first one, we would like to perform a detailed analysis of pure materials, so drugs and mesoporous silicas. Then we would like to design and optimize some encapsulation processes, and then characterize in details the synthesized samples, especially taking into account that some confinement effect may occur in these systems. In our work, we selected two different kinds of drugs. They are coming from the group of L-type calcium channel blockers and also from beta blockers. The first group are the dihydropyridine derivatives, which have a vasodilative activity and are used in long-term hypertension treatment. Because they are known since 1970s, we know already 4 generations of these drugs. Despite being highly selective, they are very poorly soluble in water and body fluids. So the application of mesoporous silica as a carrier may increase the water solubility of these substances. For beta blockers, represented by acebutolol, this kind of drugs are used in renal origin hypertension treatment this group of drugs is freely soluble in water, but inside the body undergo the first pass biotransformation, which we would like to avoid. So in this case, using the Mesoporous silica material as a carrier is a possibility to avoid this biotransformation. In general, according to the UPAC classification, Mesoporous materials has the diameters of pores in a range from 2 to 50 nanometers. There are several types of Mesoporous silica materials known all over the world. From this variety, we have chosen two types of them, MCM41 and SBA15, and they are both hexagonally arranged. They have a 1D structure of pores, but they differ in the pore sizes. Why they can be used as carriers for drugs? Because the hexagonally arranged structure of pores allows to drug molecules to be distributed quite homogeneously. They have very excellent sorption properties. They have well-defined narrow pore sizes distribution. They are highly biocompatible, low cytotoxic. They are also thermally stable, and what is also important in our study, that they can be easily synthesized or available commercially. In our study, we have two different materials. First of them, SBA15, was synthesized in our laboratory. The second one was purchased commercially. First of all, we investigated the adsorption properties of these materials using low temperature nitrogen sorption analysis. As you can see from the table, these materials differ in the pore sizes and also in the volume of pores, and they have slightly the same specific surface area. We also checked whether the structure of pores is really hexagonal. Here you can see the small angle X-ray scattering of our SBA material. A typical 3 peaks corresponds to the hexagonally arrangement of pores. We also checked whether the silica walls are built from amorphous or crystalline silica. Here you can see the back spectrum, which means that we have no crystalline peaks, so the silica wall is amorphous. And here you can also see the morphology of our materials. What is important here, as you can see, the surface of these materials is very, I would say, complex. So during the encapsulation, it is important to take into account that most of the drugs will be localized at the surface, and we must get rid of them during the synthesis. In our laboratory, we used 3 different types of encapsulation methods. First of all was the adsorption from the solution using different solvents. The second one was melting method, and the third one adsorption from the solution under reduced pressure. Due to the limited time, I'm only focusing on the first method, so adsorption from the solution. The general scheme of this process is similar in both lacidipine and acetylol. We mix Mesoporous silica material with the appropriate solution, then continue mixing for 24 hours, then filter the sample, wash them twice, and dry for 48 hours at 50 degrees of Celsius. Then we would like to know whether our method was efficient in drug loading. First of all, we used post-synthetic concentration verification using spectrophotometry, but in our case this method was not accurate because the solutions were too concentrated. So we decided to change our study to thermal decomposition using thermogravimetry. Here you can see the typical curves obtained. In both cases we've got characteristic 3-step curve. The first step may be assigned to water decomposition from the sample. The second and the third one is ascribed to drug molecules removal. So we can say that we have two different kinds of molecules with different binding strengths to the silica wall. We also wanted during our synthesis that our drug would be totally amorphous, because then it would be better soluble in water and body fluids. So we checked our drug amorphicity using two different methods. It was differential scanning calorimetry and wide-angle X-ray scattering. For the first method, we obtained some spectra. Here you can see the comparison of pure materials, the physical mixture, and the synthesized sample. Those peaks coming from the melting of crystalline substance don't appear at the synthesized sample. It means that we don't have any crystalline drug inside the silica. There are the results of Beck's measurements. They also confirmed that in physical mixture we have the crystalline form. In our synthesized sample we don't have any crystalline form of our drug. So our drug seems to be only in an amorphous state. We also wanted to know how our drug is bound to the silica matrix. In order to find it, we performed a Fourier transform infrared study. Here you can see the spectra, again for pure drug, pure silica, physical mixture, and the synthesized sample in both cases. After a detailed analysis of each bands, it turned out that two types of bands ascribed to NH stretching vibration and CO vibration do not occur in the synthesized sample. It is localized somewhere here and here. So it means that those groups of atoms are involved in the binding with silica matrix. And also we would like to check whether, because when we put the drug inside the silica matrix, the drug molecules are localized in a restricted space, and because of that we may think that the confinement effects may occur, and we expect that the effect of the confinement to be seen in molecular dynamics study. In our case, we performed the NMR line study, and as it was shown here, the third component of the line ascribed to the drug molecule is narrowing after encapsulation. It means that the drug has rather liquid-like behavior. It's not like in crystalline form. And to sum up what I've said before, in our study, hexagonally arranged Mesoporous silica materials were applied in drug delivery. We used anti-hypertensive substances. Several different methods were used. Their efficiency depended on the method and also on the type of matrix used. All the drugs were localized in the silica samples in amorphous state. And we also revealed the active sites of drug binding and revealed some confinement effects. I would like to acknowledge for founding the scholarship by the European Union, and thank you for your attention.
We have time for one short comment or one short question, so please.
Did you try to analyze the crystallinity of your materials in the already encapsulated state? using your techniques? Or a synthesized material was taken as it was synthesized?
No, it was taken after the synthesis.
After encapsulation?
Yes.
So my question then is, you also tried FTIR spectroscopy of the encapsulated material as well? Yeah?
Yes, yes.
Yes, so usually FTIR also shows the differences between the amorphous and crystalline material. So did you try to analyze the FTIR bands on this point? If successfully, you could not use other techniques for the analysis of your crystallinity. It's just simply, did you analyze?
No.
I recommend it.
Okay, thank you.
Okay. Oh, maybe short, please.
What is special role of hexagonal arrangement in your matrix? Why you need hexagonal arrangement materials?
Actually, it's not a need to have hexagonally arranged, but if you, for example, have glassy-like porous materials, the drug is distributed. You can say anything about the distribution of the drug. If it is arranged hexagonally or cubic or something like that, the arrangement is more homogeneous.
So, thank you very much again.